Hey physics peeps, Mr. McLeod here. Today I want to talk to you about the meter stick, or measurements really, but I'm going to be using this meter stick for most of what we're going to do this morning. If you guys remember in the assignment I gave you, I asked you to do some conversions. Some of them were easy. I think the third one was a little more outlandish, a little crazier. But yeah, I want to give you sort of a baseline for everything else we do in here, because there is a standard method and a standard set of units we use in physics. We call them the standard units. The SI units is another term for it. You got Standard International. Could be wrong about that. That's what I think it stands for. Anyway, we're going to start talking about distance or length to begin with. You guys see here, I hold in my hand a meter stick. So you know this is the length of a single meter. And this is the base SI unit in physics for length, for distance. That isn't saying we can't talk about smaller measurements. Like, if you get close to the meter stick here, you can see the numbered marks. Those are centimeters. I'm sure many of you already know this. And as you go even smaller, you get the little tiny tick marks there at the bottom. So, if this is a meter, and there are 100 of these numbered marks on here, we could say that those are centimeters. They are cent of a meter, or 1/100th of a meter, right? That's what cent means. Think about change and money. A cent is a penny. It's 1 penny out of 100 make $1. 100 pennies make $1. So yeah, centimeter. And then if we go down, we split each one of those centimeters into 10 pieces, known as millimeters. And those are, there are 1,000 of those for this singular meter stick. So exciting, right? Talking about meter stick at the beginning of class, but it's super important. And if we go larger than the meter, we could technically say we have a decameter. You don't hear that very often. That's 100 meters. Or well, let's just jump to the one that we actually use, the kilometer, or the kilometer, right? Kilo meaning 1,000 of these guys. So if I stack 1,000 of these meter sticks end over end over end, we would get a kilometer or a kilometer. Okay, going down once again, getting smaller. Like I said, we have centimeters, then we have millimeters, then we have millionths of a meter, which is the micrometer, or micrometer, some people call it. Billionth is nanometer. And then we start getting too small to really be stuff that we use. We get things like the femtometer, the picometer, even all the way down to the Planck length. But basically, metrics is really easy because of the fact that everything goes up in multiples of 10. So we do 10 of these is a known measurement, 100 of these is a known measurement, 1,000 of these is a known measurement, even though we only really like to use 1,000. And going down as well, 1/10 of this, 1/1,000, or 1/100th of this, 1/1,000th of this, 1/1,000,000th, 1/1,000,000th. But when we're doing physics, we want to do everything in meters. So even if I give you, let's just pick a random value here, even if I give you, let's say 19 centimeters, so let's say, actually just do a real measurement. I'm going to take this, not the right class for it, but let's take a chemistry textbook. Let's get its volume really fast. So I'm going to measure the width right here of the book, and I'm going to say that is about 23.4 centimeters. And you know what? I can't really see the lines very well, so I'm going to say 23.4 plus or minus 0.1. Okay, and we're going to talk about why I'm doing that plus or minus here in a moment as well. So the width of the book. I like to draw pictures in physics. And not only do I like to draw pictures, we kind of need to draw pictures a lot of the time in physics. Okay, and this just means these are just brackets. And I said 23.4 centimeters plus or minus 0.1, which means we are plus or minus a millimeter, about, right? So I can say, yeah, point, but we're saying in centimeters because this is in centimeters. All right, now let's talk about the length of the book. Length of the book, pop the meter stick on here real fast. Get an estimation here, 28.3. And I'm also gonna say about plus or minus 1 for that one. So 28.3 plus or minus 0.1. And remember that's centimeters, I kind of ran out of space there. And just for the heck of it, let's do the depth of the book as well. So we'll make this a 3-dimensional measurement. Well, I'll redraw it over here. This is a edge-on view right here, right? And the thickness of the book, or the depth of the book, in its 3rd dimension, is approximately we'll say 3.7 plus or minus 0.1. 3.7 plus or minus 0.1 centimeters. Okay, cool. So we have our 3 measurements. I'm gonna assume that all of you guys know how to find the volume of a 3-dimensional rectangle. By the way, what's the name of a 3-dimensional rectangle? Okay, it's called a parallelepiped. You don't hear the term very often, but that's what a 3D rectangle actually is called in its technical term. Parallelepiped. It's a weird name. Anyway, so if I were to multiply its height by its width by its depth, that would give me the total volume. And we would also have to figure out the total air. And the air adds up differently based on the way in which we're using it. If we're multiplying the numbers, we deal with it one way. If we're dividing the numbers, we deal with it another way. If we are doing exponentials. For this class's purposes though, we're just going to, well, for right now, we're just gonna add them together. Things get a little more complicated, and we're gonna try to avoid too many complicated air measurements. But Walter Lewin, MIT physicist, one of my favorite things that he says is any measurement without uncertainty is useless. And that's true. I'm going to give you an example on probably the next video that shows you that if you don't take air into consideration, how your actual values you're measuring could end up being completely wrong or completely based on air. There's no way to know unless you're actively keeping track of how much accuracy you have. And it is an estimation. Some people might see better than I can. I think the meter stick, we can agree, doesn't do any better than millimeters. So we can't say, we could technically say, well, it kind of looks like a half of a millimeter. But just to be safe, I prefer to keep it to say we can't be any more accurate than the numbers that this thing gives us. And it's safer to just say plus or minus 0.1 centimeters. All right, so the point of this, we don't want units in centimeters. Because if I were going to use this for something involving physics, let's say I wanted to use this to find density, or I wanted to use this, this is for volume, so it's a little different, or let's say I wanted to find how much the weight of this in newtons, we would have to have all of our units in what are called the SI units. The SI units are the standard units in physics, and they're convertible across the board. So some examples of those SI units would be let's make it capital I, because that's what it's supposed to be, would be the meter for length. So even if you're doing a measurement and you get an answer that's in nanometers, let's say I give you something and you get 1 times 10 to the negative 9th power nanometers, or meters, you're going to keep it that way. You're not going to convert it into nanometers because then it's usable in physics. So SI unit for, I'll write the whole word out so this makes sense, length, sorry for my cursive, maybe I should not write cursive, length is meters. The standard unit for mass is a little surprising. That's how, it's not how heavy something is, that's not its weight. We're gonna have a whole several lessons on the difference between mass and weight. But mass is measured in kilograms. Seems weird, you think it'd be grams, but we use the kilogram because it's more reasonable for the size of most things that we deal with in everyday life. We deal with fluids or liquids in liters, which is capital L. We deal with time in seconds. We don't like to deal with time in minutes or hours or years or days. Deal with it in seconds. And like I said, that's because, let's say, I need to do a bunch of measurements and I need to tell someone a force in newtons. Well, this is going to be a little of a jump start for you guys, but a newton, the unit newton, which is N, is actually the same as a kilogram meter per second squared. That's the units for the newton. And the thing about it is, if you had measurements and you did your measurements in grams, or you did your measurements in, let's say, centimeters, or if you did time in minutes, and then you tried to convert it into newtons, you'd have to go back and convert every one of those numbers into the SI units. And so in general, in physics, we want to convert everything to these units at the beginning of a problem. First thing you should do, and they're going to throw some curveballs at you just to make sure you do this in a lot of your physics problems. That's through the AP website, or that's through WebAssign. They'll give you work where they intentionally give you centimeters or minutes or something off of these, so that way they want to double check to make sure that the first thing you do before you ever start a problem is you convert all your units. Okay. Now, of course, when you talk about how to convert the units, a lot of time people that aren't used to the metric system will look up a chart, but it's not too difficult. So like, let's take these values, 28.3. I'm gonna use a different colored marker, make our lives a little easier here. Hopefully you guys can see this pretty well. Okay, so 28.3 centimeters. Okay, so one easy way to do it, 28.3 centimeters, is to think, well, there are 100 centimeters in a meter, and centi means 100, so I'm going to move 100 worth. So I'm going to move 2 decimal places to the left. So instead of, this marker's way too light, I'm going to write this in, so I'll write it in blue. So 28.3 is the same as 0.283 meters, and then we'll just say plus or minus, well, same thing, 2.001 centimeters. Now, this actually might be in scientific notation, meaning that they might move the decimal. Well, we'll talk about scientific notation if you don't know that already, but yeah, we'll leave scientific notation for a different video, just in case. So I'll leave it like this for right now. But this is the same as this number, but this number is now usable for most physics problems. Same thing with this. We're going to move the decimal over twice, and we're going to get 0.234 meters. And same thing with the depth. We're going to move it over twice, and we're going to get 0.037 meters. And the answer doesn't change, but now the answer is more usable. Because if I then wanted to know the density of the book, now density isn't covered in this class, it's an AP2 topic, because we do fluids in AP2, not in AP1. We would need to know the volume, because mass divided by volume is the density of an object. So if I were to take this textbook, I would put it on a scale, I would get its mass in kilograms, and I were to divide now by these 3 numbers multiplied together, that would give me the density of the book. If I had kept it in centimeters though, there are some charts out there, there are some people that use smaller units, but it becomes very, very, very difficult to use for anything else. So first steps would be to convert these to lengths that are usable. Anyway, so that's our basic thing on measurements. I haven't really shown you any fluid measurements or anything like that. We don't have a lot of them in here. Physics, the first physics class tends to be primarily focused on solid moving objects, going certain distances, and things like that. Yeah, so I'm gonna leave it at that. I was gonna do some coordinate systems with you guys, but I think I'll just make another quick video right after this and cover coordinate systems in a nutshell as well. And then we'll talk about things like vectors, trigonometry, stuff like that. Let's see. I guess I should give you a list of the prefixes and suffixes that we might use for the metric system. So I'm going to erase this. Isn't it great that you have a recording? You can always rewind and go back and watch me, and you don't have to go through this whole process of trying to do that. Okay. All right. So prefixes, suffixes. Well, we're not going to have any suffixes. I don't know why I said suffixes. Just prefixes. Okay, so we have the meter, we have the gram, we have the liter. Yeah, we'll just stick with those right now. And the prefixes that we'll see for that, I'm going to put right next to it in red. So we have meter going this direction for all of these. We have 1/10 of these, which is centi. Sorry if you can't see that. The handwriting's too small. I'll write a little bigger actually. Right. Centi, which just means 1/100th. Right? And then we divide by 10 again, and we get, now there is 1/10, but we don't use that one. That would be a decimeter, but you don't see decimeters. There's no mark for here but if we were to break this meter stick into 10, there would technically be another category here. Going down a little bit more, we have milli, which is 1/1000th, which is the really tiny thick marks here on the meter stick. I noticed you guys might notice that this is burned. That's because I have a death ray, and this happens to be the one meter stick I burned for death ray demonstrations. We'll talk about that another time. And then if we keep going, I'm gonna go all the way down here so you guys can still see. We're gonna say, square on that. We're going to say micro. So micrometer, or I like to say micrometer. I got in a debate with this with an engineer once. I like to call it micrometer because that's the name of the actual device that's used to measure it. Use a micrometer to measure small objects. I argued that it should be pronounced micrometer because the prefix is micro, but apparently in most fields they still use they say micrometer for the actual size itself. So it's like, oh, it's 1 micrometer, it's 10 micrometers, it's 2 micrometers, which just means 1, 10, or 2 millionths of a meter. So 1/1, 2, 3, 4, 5, 6. Look at that. Okay, micro. And then we have nano. You guys have heard of nanotech or nanotechnology. Basically, it's anything that is 1/1000th of a meter in size. 3, 4, 5, 6, 7, 8, 9. And the way I remember this is it's 1 times 10 to the 9th. And this is, so if we were going to write this in scientific notation to make it a little easier, this is 1 times 10 to the 9th. This is 1 times 10 to the 6th is micro. Centi, 1 times 10 to the to the second, and 1 times 10 to the third. I had to think there for a second for that. And that's going down, down, down. Going up the other direction, we get similar things, but we don't use very many of them. If I were to go up, I could say something along the lines of, I could say deca instead of deci. I could say decameter, decagram, decaliter, which would be 10 of those. I could say, remember the term for 100. Well, we don't really use them. We tend to jump right to kilo. right? Kilometer, kilogram, kiloliter. Yeah. So, and that would be 1,000 of each one of these measurements. Kilogram is actually, if you guys remember, the SI unit. If you're ever trying to do a conversion, I know this isn't metrics, but if you ever want to know how much something weighs in general, and you're trying to compare it to the metric system, just remember that a kilogram is about 2.2 pounds. A kilometer is about 0.6-ish miles. A kiloliter, I don't know the conversion for that to cups or ounces or whatever, but just those two. So another reason I know that is because if you run a 5K, you run about 3.28 miles. Oh, and that's another one. A meter stick is 3.28 feet, almost exactly. So meter stick is longer than a yardstick, which is 3 feet. But not only that, if you're ever trying to do, like, I like to drop things off buildings and I like to know how fast they're going, but it doesn't seem very realistic to most American students. If I were to then say, oh, it fell this many meters, it seems to make more sense, or it was going this many kilometers per hour. We like to use terms like miles per hour and feet per second and stuff like that. So sometimes I'll do a conversion like that for you, just so we're more comfortable with the answer. But we do the physics with these values right here. So we got kilo, which is 1L. I make that mistake constantly, which means 1,000. So that's, oh, by the way, over here, I made a mistake. This is to the -2 power, -3 power, -6 power, and -9 power. This is going downwards, not up. Okay, so we got kilo. After kilo, we have mega. But think about, and this is 1 times 10 to the 3rd power, or 1 with 3 zeros, 1,000 or something. This is 1 times 10 to the 6th, that's a million or something. Giga is 1 times 10 to the 9th, so the giga is basically nano. And then if you guys have computers, you've possibly heard of terabytes. I think it's 1 R. Tera with 2 R's is like the Earth. Tera. And that's 1 times 10 to the 12th, or what we say is trillion. For these type of measurements, we tend to stop here. And then if we go anywhere beyond here, we tend to start talking in terms of astronomical units. Like we'll say 1 AU, which is like, it's a weird measurement. It's basically the distance between Earth and the Sun. And we start measuring things in Earth-Sun distances. And then once we get bigger than that, we start talking about light minutes and light hours and light seconds. I'm not going to put those up there because those aren't clean numbers that we use for things. But just so you know, if you have anything that has a higher prefix, they go up like this. And it actually gets higher than that. Kilo, mega, giga, tera. I'm trying to remember the next one for quadrillion. I knew it, and my brain's just not on it today. All right. So anyway, prefix table. Well, I think we are probably good. I will post this video, and I'll get the next one up after it very shortly. Have a great morning. Mr. McLeod out.